Okay, today we'll use the Q, the heat that we've been talking about, and relate it to how much heat per mole of reaction. And we're going to end up calling this enthalpy. Enthalpy is, again, it'll be a heat unit, typically kilojoules, but you could use other units, and divided by, sometimes we'll do moles of a material, or often we'll talk about moles of reaction. And we'll further define that as we move along here. So again, here's the definition of enthalpy: the sum of the energy of the system. I know this. There's pressure in here. There's volume in here, but for us, this I think will work out better in terms of talking about defining delta H, which is change in enthalpy. And we're always going to be talking about the system in terms of enthalpy. So we don't we're not going to always be writing the SYS down or the word system. But delta H is the energy, the Q, the heat, divided by the moles of limiting reactant if it's a reaction. Sometimes it might just be a physical process, not a chemical reaction. So in those times, we'll just be talking in terms of the chemical itself. So we'll get into this later. So let's not worry about that today. But we will be worrying about this extensively for the rest of this unit. So if the system loses enthalpy, it's losing energy, and energy is a product. And we've kind of talked about that a few times in some other sections. And then the opposite of that would be endothermic, and all the opposite ideas there. So let's jump into how we could use enthalpy. What's the heat change associated with the formation of 5.67 moles of HCl in this reaction? So with a lot of things this year, factor label does us a lot of good here, and it will work out really well with this kind of question too. So we could start off with the 5.67 moles of HCl. And then in the chemical reaction, there are 2 moles of HCl in one of the chemical reactions. And we'll actually call this 1 mole of reaction. So now moles of HCl have canceled, but moles of reaction remain. But in this question, it's given to us what the change in enthalpy is. So we have a negative 184.6 kilojoules per mole, and it's always going to say mole here. Well, typically it's going to say mole there, but you have to know that it is in terms of molar reaction because it's listed with the rest of that. So again, someone should put down moles of reaction, but they don't. So we'll have to assume that that's going to be moles of reaction. So I think we get almost everything to cancel here. Moles of HCl, moles of reaction. And so we just have a little bit of multiplication and division to get us into an answer. And the only thing we have to really go by for significant figures is the measurement that was given. I guess we don't know where the origin of that delta H is from, if that is a theoretical or if that was a experimental. So I would stick with the 5.67. So I think that's going to give you somewhere in the range of that. And we could do a couple things here because this is heat. So some people will do that. That's okay. But I think most people would actually say that. Okay? It's up to you. But you have to kind of be able to recognize both, because maybe I tell you, or you read a question in the textbook or on a test, and it says 523 kilojoules of energy was released. Well, you have to know what that means. And so what that means is negative 523 kilojoules in terms of if we're doing some kind of mathematics with that. Let me move this up just a little bit here. Okay, so many of these questions we can use that factor label technique, and I think we're going to be able to use it with this question also. So you could dive in a couple different spots here, but I'm going to start off with the 87.9 grams of SO2. And the molar mass is given to us, so that's nice, so we don't have to worry about that. Well, we don't have to worry about figuring out what it is. And then in the chemical reaction, there are 2 moles of SO2 in 1 mole of reaction. And then again, we're given the delta H. Now this question already says the evolved. So once you get into words, we don't have to worry about signs. Actually, we can't worry about signs, because you keep that negative there with the word evolved or released or whatever other words you can kind of come up with there. That's kind of a double negative, and you've kind of done a 180 with your answer there. So again, if words are introduced there, we're going to leave the signs out. So because the words are already designating the sign. And again, we don't know the origin of this delta H as far as calculated, theoretical, or if it was some kind of experimental. So I'm going to use the 87.9 as my significant figure starting point there. And I get 136 kilojoules when I do that math there. Evolved. So again, factor label can get you pretty far in this course. I think we're going to be able to use it again. I don't think I'm going to need all that room here, but let's jump in. So you could jump in with the 3013 or negative 3013, but it uses the word evolved again. So we're going to leave the negative out of that delta H. So I'm going to start off with the 266 grams of P4. You're going to have to go on the periodic table and find that molar mass. And then typically I wouldn't write this down, but I'm going to write it down today. In 1 mole of P4, there's 1 mole of reaction. And then we got the 3013 kilojoules in 1 mole of reaction. So let's go with an answer of 6,470 kilojoules of energy or heat evolved. Okay, so all factor label there. So you really didn't have to know too much about heat, about enthalpy. Mostly you had to be able to factor label. Okay, a little bit of not much of a misprint here, but it says question 1 of 3. I lied, it's question 1 of 4. So there's actually 4 of these here. So this is a free response question from a number of years ago, and all the answers are on the next slide. So I'm not gonna write any of the work down. We'll kind of go back and forth between these two things. I might kind of circle a few things or highlight a couple things. So this material is available to us here. A few of these things are just safety items. Lab coat, goggles, gloves. They are going to be super important if you and I are in the lab, but as far as most of these AP Chem questions, not significant. We have some HCl, we have some sodium hydroxide. It looks like we have various molarities of that. We have the insulated cup with a cover, we have a stirring rod, and we have a thermometer. That's very typical for any of these thermochem questions, calorimetry. And we have some distilled water. Okay, so we also have some glassware. So we have a flask, we have a beaker, and we have graduated cylinder. So of those three, beakers are great to contain liquids, to transfer liquids, to mix liquids. They are terrible at measuring liquids because that's not very much precision there. So you can go from 0 milliliters to 10 to 20 to 30. This graduated cylinder, on the other hand, you can go from 0.9 to 1, 1.1, 1.2. There's a lot more precision involved there. Okay. So part A, we got student selects 200 milliliter beakers, measures out 50 milliliters. That is a mistake right there. So we didn't even get the question yet, but I would not use any any beakers to measure out liquids. Measure the initial temperature. Student pours the two solutions into the insulated cup. That's a good method. Stirs, covers, records maximum temperature. So those are all sound practices for calorimetry. The question A1, is the experimental design sufficient to determine the enthalpy of reaction to a precision of two significant figures? Well, I think I've pointed that out, that using beakers to measure liquids is not going to have sufficient precision. So you'd have to use a graduated cylinder to be able to get to where you'd want to go to be able to get an answer that's going to be, in this case, significant. We'll get to the answers, and we'll double check how we did here in a little bit. List two specific changes to this experiment that will allow, so we need two changes. So one change I said was use the graduated cylinders. So let's talk about what we're actually trying to accomplish here. So we're trying to, with calorimetry, solve for Q. So if we are able to measure to more decimal places, that is going to impact the measured mass. We can't do anything with C. Specific heat is the specific heat. We can't change that. But if we want to be able to get possibly more significant figures, if we get something that has a greater answer, we might be able to get more significant figures. And if you would have a greater change in temperature, so let's go to a small change. If we had, well, let's go with the one we had here. So we had 24.5 was the initial temperature, and the final temperature, you know what, let me erase this and I'll write it as delta T. So 29.9 minus 24.5, that equals 5.4 degrees Celsius. So that's going to give us two significant figures. So when we get that Q answer, we're just going to be able to get two significant figures out of that. Is there a way we could get 3 significant figures out of that? Yes. We can't do anything with the initial temperature, but we could have made this final temperature a lot more dramatic. What would have happened if it would have been, instead 29.9, 59.9? So in that case, we would have got 35.4. And that now is 3 significant figures. So I think that would have worked. So I think we'll look at the answers and see what they say. So part A, and here is our part A. And I think that would have worked. They also mentioned, by the way, another possibility, that instead of using 1 molars, you could use 2 molars. And with that, you would have been reacting more material, and that would have gotten you the bigger delta T. So I just mentioned in terms of delta T, but they gave us a more specific way of getting that greater delta T. So I think I probably should have thrown that in there too. Okay, so let's double back here and see what we got for part B. So in part B, second student's given 2 solutions. Student pours the solutions into the insulated cup. Okay, it's very similar to last time. Student calculates the amount of heat evolved in the experiment to be 4.1 kilojoules. So their Q equals Cm delta T. Answer was 4.1 kilojoules. Calculate the student's experimental value for the enthalpy of reaction in kilojoules per mole of reaction. So how do you take the Q and turn it into delta H? So we have, again, a kilojoules, but we want a kilojoules per mole of limiting reactant. Well, both of these are exactly the same amounts, and they're a 1-to-1 ratio in the chemical reaction, so they're both the limiting reactant. So it doesn't really matter which one you pick, but if you take the molarity and volume and turn it into moles, and have the 4.1 kilojoules on top, put the moles of limiting reactant on the bottom, I think that's going to work out. And maybe with B, we'll kind of jump back and forth and see what we got there. So it looks like that's what they did. So they got the moles of limiting reactant, and then they divided that. Well, they had the kilojoules and divided by the moles of limiting reactant. And the sign here is very important this time. We have to think about what's going on. So when you do calorimetry, that is the surroundings. So the Q, how much heat the water that's in the calorimeter absorbed. And if the temperature of the calorimeter, the water in this calorimeter went up, that means it absorbed energy. That means the system lost energy. So hence this negative here. And I think that's a challenge in thermochemistry, is to remember about the signs. Part 2, student assumes that the thermometer and the calorimeter do not absorb energy. Well, we know that that's not true. The thermometer and calorimeter do absorb energy. Does this assumption result in a calculated value of the enthalpy of reaction that is higher, lower, or the same? Well, I'm almost positive it's not going to be the same. And if we look at what we're supposed to do, so the student thinks you just do that. But you should always take into account the C-cal. So I think that's going to give, if you don't take into the C-cal, that's going to impact this Q answer, and it's going to make it a little smaller than it should be. And if that's smaller, then the delta H is going to be smaller. Let's double check. Let's see what these guys say here. So they do say lower, and they give you a number of different kind of scenarios as to why. But I think the reasoning that I gave is going to match up with that. This part 3, you are not prepared to answer that yet. This was an AP question. They assume that you've learned the entirety of AP Chemistry, which we haven't at this point. So we're going to skip that part. Part C, a third student calculates the value for the enthalpy of reaction that is significantly higher than the accepted value. So we need a specific error. By the way, very rare that these guys tell you not to do this. But don't do it. Don't do it on a lab report. Don't do it on a test question. Don't do it when you're talking with your friends. So we need a specific error. So let's just go straight to what these guys said. So this is the part, by the way, that we don't know how to do yet. So that was that part we skipped. So let's move on a little bit here. Okay, student read the thermometer incorrectly, so they got a delta T. That might have been incorrect. That would have worked. If you mixed up your amounts of materials, in this case, the molarities, if you have greater molarities, you're going to actually be reacting more solute than you were expecting to. And then here's the second part of this. We can check that out. This just goes back. This second part here goes into where that math would impact your answer. So I think these two really go hand in hand with each other. Okay, a little multiple choice. I might have to, no, I guess I won't have to make that smaller. So with all these multiple choices, I think I've already always given you guys the answers, but let's figure out what we're doing here. So we have a metal. We heat it to a very high temperature. And then we put it into a calorimeter that has water, and the water is at a low temperature. And when they get to a equilibrium, they get to 35 degrees Celsius. So what's going on here? So the metal goes from 100 down to, I'm just going to leave these both as positive answers here, goes to from 100 to 35. So what's that? A change of 65 degrees Celsius. And the water goes from an initial temperature of 22 to a final temperature of 35. And that's only a difference of 13 degrees Celsius. Yeah, one's going up in temperature, one's going down in temperature, but I'm leaving both these for the purpose of this question as both positive changes. Which the following could be concluded. So a couple things before we actually get into it. Q equals Cm delta T. If you were going to do this mathematically, you would have to do this for the water and solve for Q. Then Q equals Cm delta T again, this time for the metal, and typically you'd be solving for the specific heat of the metal. So how and why you're doing this? Because this happens. Energy cannot be created nor destroyed, it gets transferred. So all of the energy that the water gains, it gets it from the metal. So if you know the heat of the water, you know the heat of the metal. If you know the heat of the metal, you know the heat of the water. So let's just go through these. The metal temperature changed more than the water. Okay, that's correct. Therefore, the metal lost more thermal energy. That's incorrect. They have to have the exact same energy. The Q's are the same. The delta T's are different. B, the metal temperature changed more than the water did. Okay. Metal lost the same. Bingo. So once we get an answer we like, we're not moving past that. Another multiple choice. Let's make that just a tad smaller. Oh, there's 2 questions there, so we don't have to make that smaller. Okay, so we already do have the answers though. We got B and we have A. So let's figure out what's going on with those. Okay, so student conducts an experiment. Delta H for the reaction between hydrochloric acid and sodium hydroxide. They do 2 trials. It looks like that same molarities, but not the same volumes. I don't think we may not have to worry about this, but 50-50 of 0.1s, that means they're both exactly the same moles. They're both the limiting reactant in trial 1. In trial 2, there's less sodium hydroxide, hence sodium hydroxide is the limiting reactant. So it turns out that they're both having the same amount of limiting reactant in both trial 1 and trial 2. This question I don't think is going to deal with that. They don't have the same volumes. So in trial 1 you use a total of 100 milliliters. In trial 2 you use 150 milliliters. So I'm just trying to think about which direction this question could be taking us. And it says amount of heat released for trial 1 is X, for trial 2 is Y. Since they both have the same limiting reactant, the same amount, they're going to be able to react in the same exact amount of chemical reaction. So they should theoretically release the exact same amount of heat. Now, will the change in temperature be the same? For trial 2, there's more volume, more grams, in this case for Q equals Cm delta T. There'd be more M that you'd have to worry about there. Let's see. But because you have more M, it's going to take more heat to get the same delta T. So this delta T will actually be less. Those are a lot of different things to think about, and probably the question is only going to deal with one of those. Which of the following, I'm looking at the question, the last part here, which of the following best explains the relationship between X and Y? And I had already mentioned that because they have the exact same amount of limiting reactant, they're going to have the exact same amount of heat released. And that mentions that. Okay, the second one looks like this is mathematical. Now, or a tricky part to these is that when you take the multiple choice section of the AP exam, you do not get to use a calculator. So we're going to have to work on our mental math here. We have sodium hydroxide, and we have hydrochloric acid, and we have the polystyrene container, that's a coffee cup, and we have a change in temperature, and it wants us to solve for delta H. So that means we're going to have to go and do Q equals Cm delta T. Once we get the Q, if we divide that by the limiting reactant moles, that will give us delta H. So there's some math here. So what do we have so far? We have a specific heat, 4.2. We have volumes, 10 milliliters and 10 milliliters, that's 20 milliliters. And that's going to give us, unless told you otherwise, and actually it is told to us, the density is 1 gram per milliliter. So that means we had 20 grams, correct? And what else do we have here? We have 26 degrees Celsius minus 20 degrees Celsius. So I guess that is 6 degrees Celsius. Okay. Let's see what we got here. This is going to be tricky to do this without a calculator, But if you would decide to use this instead of a 4.2 as a 4, or 4.5, just round it to something you like. You could also make this a 5. That might be able to work out for you. Why can we do that? Well, we only have 4 answers. We only have 4 answers to deal with here. If you had a calculator, if you wanted to do it longhand, I think it's going to give you, it wouldn't be crazy. It'd give you that. Okay. And then the moles of Lin reactant, we have 1 mole divided by 1,000 milliliters times the Lin reactant volume, 10 milliliters. Okay, so we got that. So let's see what we got now. And let's see if we're going to like this or not like this. Actually, I bet you're not going to like the math without a calculator. That's a little decimal place there. So we know that B cannot be right because that had a 2-5 in it. And we know no matter what's going to happen with these decimal places, we're going to have an answer of 5. Something with a 5. Here's what you could do. You could, let's move some decimal places. 1, 2. If we move that 2 decimal places, that means we have to move the other one by 2 decimal places. So that would give you 50.4 kilojoules divided by 1 mole. There we go. Now I left that negative out. This Q was heat released because the temperature of the water went up by 6 degrees. So if the surroundings went up in temperature, the system lost that much energy. And this is our last question. I think it's our last question. Yeah, and the answers are already there, but let's go through it a little bit. We have 1 mole of aluminum. It's at 298 K. The melting point of aluminum. So it looks like we're going to have to worry about a couple things. Heat of fusion of aluminum is, so to melt the aluminum, to make it go from a liquid, a solid to a liquid, we're going to have to use that 10.7 kilojoules per mole idea. And then we also have heat the solid. We have to heat it from 298 up to 933. And we might have to add those together. Calculate the amount of heat needed, yeah. So actually, let's go check out their answers. Okay, so the 24 kilojoules per mole Kelvin, that's the heat of fusion. And they do they have the right units there? 10.7. Whoops, I'm looking at the wrong spot here. Molar heat capacity, sorry. Apologies. So 24 joules per mole Kelvin. That's related to a specific heat. A little bit different units there, but so 24 joules per mole Kelvin. We had 1 mole of aluminum. So those canceled. And we had a change in temperature. So this is like a Q equals CM delta T. Similar, except we don't have grams there, we had moles. So the Kelvins cancel. We're left with the joules, but let's get it into a kilojoules. And then we also were given the 10.7 kilojoules per mole, and we had 1 mole, so 10.7 kilojoules we're dealing with for the melting part. Add them together, and we get 26 kilojoules. Okay, factor label for the most part, a little bit of Q equals Cm delta T. And then the last part of this, the equation for the overall process of extracting. So for part A, that was for, I guess you could call that recycling. If you wanted to extract it from aluminum oxide, how does that compare with the recycling? So that means we have to get this into the same kind of units. We needed to get it into, we need to get it into a kilojoules number. Right now we have a kilojoules per mole of reaction. So here's our reaction, and it looks like there's 2 aluminums in every reaction. So let's do a little conversion there. And I did that, and they get this number. So how does 26 kilojoules compare with 837.5 kilojoules? Well, I think one is way less than the other. So in this case, recycling requires a lot less energy than extracting. Okay, I think that concludes today.